All the physics we've been studying up till now was well known even at the late in the 1800s. So now we want to try to bring our physics knowledge into the 20th century, maybe even 21st century. So we're going to study a couple of things that have been known collectively as modern physics. And physics really advanced as the subject of study became at the tiniest levels of nature. So let's see what there is. We've been studying waves and sound and light as a wave, and by the end of the 1800s it really did seem like light was completely explained as a wave. However, there were some developments early on in the 20th century, some phenomena as they were studied, that seemed to give the idea that light is a wave some problems. So we're going to look at a couple of those. I want to talk about two phenomena that were well known that gave light as a wave real problems in explaining. And the first one is called the photoelectric effect. And the photoelectric effect is simply that when light shines on certain types of materials, electrons are emitted. So photocells, like in calculators, solar cells, they operate by the photoelectric effect. When light falls on those materials, electrons are ejected. The picture of light as a wave does not do a good job at all in explaining the characteristics of the photoelectric effect. And it turned out that Albert Einstein used a picture of light as particles instead of waves to explain the photoelectric effect, and actually his theory was worked so well that he won the Nobel Prize in 1921 in physics. Another effect that gave light as a wave problems was the Compton effect. And the Compton effect was discovered when Arthur Compton, American physicist, was studying the interaction of X-rays, which are a band of electromagnetic waves, of which light is exactly the same kind of thing, the interaction of X-rays with atoms. And he found that the wavelength of the X-rays changed when they interacted with atoms. And the picture of light as a wave was unable to explain the things that Arthur Compton saw. But when he considered light as behaving as a particle instead of a wave, his results were perfectly explained. So it appeared that at the atomic level, energy and matter exhibited the characteristics of both waves and particles. So if you ask the question, is light a wave or a particle? The answer was yes. So it appeared that an entirely new theory, entirely new picture of light was necessary. Now we're going to talk about another phenomenon that was well known at the time, but whose full explanation required a new picture of light. And this is the idea of line spectra. And we're going to be talking in particular about the line spectrum of hydrogen. So first of all, let's just explain what it is, what we're talking about. If you have a source of light, and you let that light fall through slits and go through a prism, what we know very well is if you let white light, for instance, go through a prism, you would get a rainbow. But it was well known that if you let light from hydrogen gas go through a prism, you don't get a spectrum. You only get, in the visible region, just these four lines. And the question was, why do you only get these four lines instead of getting an entire spectrum? So for instance, if I shine hydrogen light through a prism, why don't I get some orange too? And why don't I get some yellow too? And why don't I get some of this kind of green here? And why don't I get all the colors? Why isn't this all filled in with color? Why do I only get just these four colors? And that was a real puzzle. Now once it became known that if you shine light from hydrogen gas through a prism, you get only these particular colors, people had the idea of taking gas of all of the other elements and sending them through prisms to see what would happen. And it turned out that what you would see is colored lines, but of all different wavelengths. So as you click on different elements here in the periodic table, you would get these characteristic patterns of colors, of specific wavelengths. And the black area between the colors was just as interesting. Why are those colors missing? So some of them were very complicated, and some of them were very simple. But these were almost like fingerprints for each of the elements. The elements could become identified by these colors alone. So there's mercury, and then we'll end again with hydrogen. And in fact, helium was discovered. Helium is from helios, for sun. This element was first separated out on the sun by its spectrum, its particular characteristic set of wavelengths. So every element was known to have this pattern, but the question was, why are there only these colored lines? Why are all these colors missing? And why is that characteristic for every one of the elements? So that actually was a very big question. And it turned out that the answer to this question only came about with a new and different picture of light. And so next time when we talk, we'll go into more detail about what was the new picture of light that ended up explaining this whole thing.